Have you ever looked at a chemical reaction and thought, it's just doing its own thing, completely out of your control? Well, what if I told you there's a simple, super powerful rule that lets you actually boss a reaction around? A way to push it and pull it to get exactly what you want. Today, we're going to master Le Chatelier's principle.
So here's our game plan for today. We're going to start with the main idea, what I like to call the stubborn systems rule. Then we'll dig into the three big factors you can change: temperature, pressure, and concentration. After that, we'll cover a couple of common exam traps to watch out for, and we'll wrap it all up with the ultimate equilibrium cheat sheet.
Okay, first things first. To really get this principle, you need to imagine that a chemical system at equilibrium, well, it has a personality. It's found its happy place, this perfect balance, and honestly, it's a little bit stubborn. It really does not like to be disturbed.
So what even is equilibrium? A lot of people think it means the reaction has just stopped. Nope, it's a dynamic balance. Think of it like a seesaw. The reactants are turning into products at the exact same rate that the products are turning back into reactants. So the levels on the seesaw stay constant, but the action, it is nonstop.
And this is where Le Chatelier's big idea comes in. The principle is shockingly simple. If you mess with a system that's in balance, if you apply a stress, the system will shift to undo whatever you just did. It fights back. That's why I call it the stubborn system rule. You push it, it pushes back. You heat it up, it tries to cool itself down. It's this beautiful, predictable push and pull.
All right, let's look at our first type of stress, temperature. This is one of the most powerful tools you have to control where a reaction goes. Let's see how our stubborn little system deals with the heat.
The best way to think about this is that the system has its own internal thermostat. So if you turn up the heat from the outside, the system goes, whoa, it's getting hot in here, and it will shift in the direction that absorbs that extra heat. That's the endothermic direction. And of course, if you cool it down, it does the opposite. It shifts in the direction that releases heat to warm itself back up, the exothermic side.
Let's make this totally real with a classic example. Here we've got dinitrogen tetroxide, which is a colorless gas, in equilibrium with nitrogen dioxide, which is a nasty brown gas. The most important part here is that the forward reaction, going from left to right, is endothermic. It soaks up heat.
So watch what happens. When you heat the flask, the system wants to cool down, right? So it counteracts that stress by favoring the endothermic reaction to absorb all that extra heat you're adding. That shifts the balance to the right, and you get more of that brown NO2 gas. And when you stick it in ice, the opposite happens. The system shifts left to release heat, and the gas becomes colorless. We are literally controlling the reaction's color with a hot plate and an ice bath.
Okay, next up, our second stressor, pressure. This one is all about physical space, how crowded the molecules are. And just a quick heads up, this rule really only matters for reactions that involve gases.
You know, the logic here is actually super intuitive. When you increase the pressure, you're basically squeezing the container, right? You're giving the gas molecules less room to move around. So how does our stubborn system fight back? It tries to make more room for itself. And the easiest way to do that is to shift to the side of the reaction that has fewer molecules of gas. Fewer particles means less crowding, which means lower pressure. And this isn't just some textbook theory. Let's look at one of the most important industrial reactions on the planet, the Haber process. This is how we make ammonia for fertilizers that feed billions of people. And managing the pressure is absolutely critical to making it work efficiently. The trick is so simple. Just count the gas molecules on each side. On the left, we've got 1 nitrogen molecule and 3 hydrogen molecules. That's a total of 4 gas molecules. On the right, we only have 2 molecules of ammonia. So, if you crank up the pressure, where does the system go to relieve that stress? It's going to shift to the right, to the side with fewer molecules, and you end up making more ammonia. It's exactly how it's done in giant chemical plants.
All right, time for our third and final factor, concentration. If temperature is the thermostat and pressure is about space, then concentration, well, it's just like a chemical seesaw. It's all about adding or removing stuff.
This analogy makes it almost too easy. Just picture your reaction as a perfectly balanced seesaw. What happens if you dump a bunch more reactants on the left side? The seesaw tips, right? To get back to balance, the system has no choice but to shift to the right, using up those extra reactants to make more products until it's level again. Same thing happens if you remove a product. The system shifts right to replace what you just took away.
Now this digging analogy helps us understand why that shift happens. At equilibrium,
The guy digging the hole, making products, is working at the same speed as the guy refilling it, making reactants. The level stays the same. But if you add more reactants, it's like you've given the digger on the left a mountain of dirt. He starts digging like crazy. To keep up, the refiller on the right has to speed up too, which means the rate of product formation goes way up. It's all about rebalancing those rates.
Okay, now for a really important part. We know the rules of the game, but let's talk about a couple of common traps that always seem to catch people on exams. Knowing these will put you way ahead of the curve.
Trap number 1 is the catalyst. So many people think that if you add a catalyst, you're going to get more product. That is absolutely false. A catalyst is like giving both of our diggers bigger, better shovels. They both start working way faster, so you get to that balance point, the equilibrium, much, much quicker. But the final position of that balance, it doesn't change one bit. It just speeds up the forward and the reverse reactions equally.
And here's the slightly trickier one. What if you add an inert gas, something unreactive, like argon, into the container? The total pressure inside goes up. So your first thought might be, oh, it'll shift to the side with fewer moles. But it doesn't. And why not? Because the partial pressures, the individual pressures of the gases that are actually in the reaction, they haven't changed at all. The argon is just an innocent bystander taking up space. Our stubborn system doesn't feel any real stress, so it just ignores it and does nothing.
Phew! Okay, we've gone through temperature, pressure, and concentration. Let's pull this all together into one powerful summary. Think of this as your personal equilibrium cheat sheet. This table has everything you need. If you increase the concentration of something, the system shifts away to use it up. You increase the temperature, it shifts to the endothermic side to soak up that heat. You increase the pressure, it shifts to the side with fewer gas moles to make more room. And a catalyst? No change to where the equilibrium ends up, it just gets you there faster. See? It all comes back to that one single idea: the system is stubborn, and it will always fight back against the change you make. And I'm going to leave you with this one piece of advice. This is the golden formula for acing this topic. It is never, ever enough to just say the equilibrium shifts right. You have to explain why. You have to say it shifts right in order to counteract the increased temperature by favoring the endothermic reaction. Explaining the why shows you actually understand the principle. So the next time you see a chemical reaction, don't just watch it happen. Ask yourself, how can I boss it around?